This video is for Chemistry in the Earth System, Unit 4.1, Chemical Reactions and Equations. Today's essential question is, how can you represent chemical reactions using chemical equations? Our first main idea, writing and balancing chemical equations. Scientists use chemical symbols to represent the elements. They use chemical formulas to represent compounds. And in a similar way, they use chemical equations to represent chemical reactions. One way to represent a chemical reaction is by writing a word equation. The word equation separates the names of the reactants from the names of the products using an arrow. The arrow can be read as yields or produces. If the reaction involves more than one reactant or product, a plus sign is placed between the corresponding reactants or products. The word equation that represents the synthesis of water from hydrogen and oxygen is on your screen here. Hydrogen plus oxygen, arrow, water. The formula equation is written by replacing each name with the chemical symbol or formula that represents that substance. Hydrogen and oxygen are both elements that exist at room temperature as molecules rather than single atoms. So the formulas H2 for hydrogen gas and O2 for oxygen gas are therefore used instead of just H or O in the equation. The formula equation is shorter than the descriptive word sentence, and so it also provides a visual description of the chemicals involved. Now, a key principle in writing formula equations is to ensure that they are balanced. The formula equation that we referred to previously is still incomplete. Notice that there is one less oxygen atom on the product side of the equation than on the reactant side. We know that the oxygen atom did not simply disappear, so it must be accounted for in the equation, as we see in the animation on the screen here. During the synthesis of water, the chemical bonds of the hydrogen and oxygen molecules break. The atoms form new bonds as they reorganize to form water molecules. Each atom from the reactants becomes part of the product. So, to make sure that all of the atoms in the reactants and the products are accounted for, the formula equation must be balanced. A balanced equation shows the same number of atoms of each element in both the reactants and the products. So, to balance a chemical equation, coefficients are placed before the chemical formulas. So, for the synthesis of water, a coefficient is needed before the water molecule. This will balance the oxygen atoms. So we have 2 oxygen atoms on the right, 2 oxygen atoms on the left. But notice that the subscript for oxygen in the H2O has not changed. Subscripts should never be changed to balance an equation. Changing a subscript would change the chemical formula, and the equation would no longer represent the same chemical reaction. Now we know that 2 water molecules have been formed for each molecule of the reactant, but the equation is still not balanced. Due to the coefficient, there are now 4 hydrogen atoms on the product side of the arrow because we added a coefficient of 2. But now there's still only 2 hydrogens on the reactant side. So 2 more hydrogen atoms are needed in the reactant side. So a coefficient is placed in front of H2, and this balances the hydrogen atoms. Sample problem. Write a balanced chemical equation for the formation of potassium chloride and oxygen from the decomposition of potassium chlorate. So the reactant for this decomposition reaction is potassium chlorate. The products are potassium chloride and oxygen. The word equation for this reaction is potassium chlorate. Reacts to form, or decomposes into, potassium chloride and oxygen. The formula equation for this reaction is KClO3, arrow, KCl plus O2. So there is 1 atom of potassium on each side of the equation. There is also one atom of chlorine on each side of the equation. However, there are 3 oxygen atoms in the reactants and only 2 in the products. The least common multiple of 2 and 3 is 6. We can balance the oxygen atoms with the coefficients so that 6 atoms of oxygen are on each side of the equation, leaving us with 2 KClO3 arrow KCl plus 3 O2s. So now that the oxygen atoms are balanced, however, the potassium and chlorine atoms are now not. To resolve this, we can simply place a coefficient in front of KCl, leaving us with a final answer of 2 KClO3 arrow 2 KCl plus 3 O2s. Conservation in chemical reactions. The equations for chemical reactions always balance because they follow the law of conservation of matter. During a chemical reaction, matter is neither created nor destroyed. Each atom from the reactants is used in the products. Each atom has mass. A balanced equation, therefore, also shows that the mass of the reactants equals the mass of the products. However, the number of molecules is not always conserved during a reaction. This is evident from the equations for the synthesis and decomposition reactions. Writing net ionic equations. A balanced equation provides information about a chemical reaction. One important piece of information is the matter state of each substance involved. By convention, the symbols S, L, G, and AQ are used to distinguish these states. Displacement reactions often involve ionic compounds in water or aqueous solution. Solid ionic compounds, however, may not be reactive at all. When dry crystals of table salt, for example, do not react with other compounds, it is because they are in this solid state. But when an ionic compound is dissolved in water, its ions can now move throughout the solution and interact with other ions. So, if sodium sulfate and barium nitrate are both dissolved in water and then combined, the reaction is described by the equation on your screen here. One of the products will be in the solid state because it has formed as a precipitate. The sodium nitrate remains dissolved in water. The solubility rules identify barium sulfate as insoluble. It seems as though 2 compounds should be formed by this reaction. However, remember that when ionic compounds are dissolved, their ions move freely throughout the water. The reaction of sodium sulfate and barium nitrate could also be described with the equation on your screen here, with each ion completely dissociated from the opposite charge. We see that the sodium ions and nitrate ions have not changed at all. Each ion is dissolved in water before and after the reaction. Ions that are unchanged during the displacement reaction are also known as spectator ions. These ions watch the action but do not participate. So, since they are not involved in the reaction, the spectator ions can be removed from the chemical equation. The resulting net ionic equation shows only the substances that take part in the reaction, according to the equation on the screen here, which represents the 2 ions in solution reacting to form a precipitate. Let's take a look at a sample problem. Write the net ionic equation for the reaction that occurs when a piece of zinc metal is placed into an aqueous solution of copper 2 sulfate. The reactants include an element and an ionic compound in solution. This reaction is therefore a single displacement reaction. Referencing a reactivity series, zinc is above copper in the reactivity series, so a reaction will occur. the zinc will replace the copper to form zinc sulfate, according to this equation on your screen. The total ionic equation is shown on your screen here, with each ion separated out. The sulfate ion is unchanged during the reaction. Therefore, we can remove the spectator ion to find the net ionic equation. At this point, you should be able to generate a full and appropriate response to today's essential question. How can you represent chemical reactions using chemical equations?